Students, casual observers, interested parties. Um, if you're in my if you're in my class, we spent some time talking about something very important, and that is that for systems that contain objects that interact with each other, well, what we already know is that momentum of that system has to be constant. Total momentum has to be constant. Or we said the net impulse of the system has to be zero. And the reason that is because the net force on the system is zero. Because each object does exert a force on the other, but those forces are equal and opposite. They're a force pair, parts of a force pair, and therefore their sum is zero. And we use that idea to talk about or to justify and derive the fact that no matter when you look at a system, well, if the system experiences no net force and no net impulse, the system maintains a constant momentum because it has to maintain a constant velocity. And so, what it can become important for us to be able to do is to find the velocity of the system. Now, when I say the system, I also refer to this idea of the center of mass. Because what is this system? Well, this two-object system can be also represented as a single point mass. And where is it located? Well, we have an expression for where to find that center of mass. All right? And what we do with that is, well, I'll put that expression for the location of the center of mass right here. And what we said is what you have to do is sum all the products of mass and position and then divide by the sum of all the masses. There's a few ways to look about that, but you can, one way we talked about today is it's analogous to doing, really analogous to doing a net torque, analogous to a net torque analysis. Except we don't worry ourselves so much with force like torque does here. We just concern ourselves with mass, so, whatever. But what this says is, well, we can look at where each object is. This is a position of each mass m relative to a chosen origin. And when I say each mass m, well, I mean that mass m. And this, the position of the center of mass, is, well, that's what it is. Position of Cm relative to a chosen origin. Chosen origin. Sorry. Relative to chosen origin. Now, so that, if you're in my class, we spent some time with previously, but what this can serve as is a little jumping off point for us to show, well, how we can derive an expression for the speed, or the velocity, really, of the center of mass. All right? And what that looks like is, well, what we really can do is just say, well, if I want the position of the center of mass, that deals with the position of each mass. But what I want is this velocity of the center of mass. And we do something very similar, but what we're actually doing, I'm going to ditch this stuff just to get it out of the way. And this. Bye-bye. Bye-bye. Get out of here. What we're really doing is we can say, well, what about if we looked at the rate of change of the position of the center of mass? Well, we'd have to look at the rate of change of the position of each mass. Well, and this is VCM, delta x over t. So we do the sum of the mass times not the position, but the rate of change of the position. Oh yeah, that's the velocity of each of those masses. And we divide by the sum of the masses. Well, what is this really but a statement that says the velocity of the center of mass is really the sum of all the momenta, momenta divided by the sum of all the masses. All right, so there's the quote-unquote easy way to find a system's center of mass velocity. Now, what you're really doing, some of you noticed, or some of you, we mentioned this in at least one of my groups today, is what we're actually doing here is, in effect, treat any potential interaction as a hit and stick and find the final velocity. Because, you know, if we do a hit and stick thing, well, what we always say is, I mean, let's see, what, just so I'm sure here, yeah, this, you know, these two objects would stick together and then move that way. And, well, especially when we say they stick together, then we're really just sort of treating them as one point mass that, you know, that moves that way. Well, and that's our whole point of this. What we're talking about here is that the system can be approximated as a point mass whose velocity, what we call the center of mass velocity, remains constant. It has to remain constant because of the system, right? This is the system. It's just a point mass. That system experiences no net force and no net impulse, so the system maintains this constant velocity, right? So let's use this approach to find the center of mass velocity of this system. Excuse me. So let's see, VCM is net P divided by, total momentum divided by total mass. Well, this object here, a momentum of 12 kilogram meters per second to the right, plus this object here, a momentum of 8 kilogram meters per second to the left. Make sure we account for sign here, people. Momentum, a vector quantity, direction of the utmost importance. The net mass, the sum of the masses, to 8 kilograms. All right, VCM, 12 minus 8 is 0.5 meters per second, positive 0.5 meters per second. So it says that this system has a center of mass velocity of half a meter per second to the right. Okay? And it also says that no matter what happens later, or at any other instant, as long as these are the two objects that are interacting, and there's no other interactions that take place, this two-mass system will have that center of mass velocity. If they whack into each other and stick together, if they whack into each other and bounce apart, if they whack into each other in a variety of ways where, you know, various amounts of energy might or might not be lost, the center of mass velocity will always be that. To the right. Okay? All right, so, you know, who cares? All well and good, right? But, yeah, I mean, to what end? So why bother? All right, well, the why bother is because this can tell us what happens in a certain scenario that is hard to analyze otherwise. All right, but what we have to be able to do if we want to handle that certain scenario, which we'll get to in a minute, is we have to be able to look at this system from different, what are called frames of reference. All right, you have to imagine yourself being able to observe this system, well, from a, well, not the typical, you know, standing on the floor, motionless, stationary observer sort of existence that you're used to. All right, and when we do that, something really cool happens. So, you know, let's look at what we call the laboratory frame of reference here, which is me standing here on the floor, everyday life, stationary. Here I am. Just so if we want to analyze the system from that frame of reference, um, initially there's a net momentum, we could say, of, well, let's see, 12 to the right, 8 to the left, 4 kilogram meters per second to the right. You get me? This has 12 kilogram meters per second this way. This has 8 kilogram meters per second that way. Yeah? Well, what did we just figure out? We just figured out what happens in the end. Because no matter what, the system experiences no net impulse. The system's momentum is conserved. The system, regardless of what happens during or after this interaction, the system has to have the same total amount of momentum. All right. We also said, we calculated a minute ago, that the VCM is 0.5 meters per second this way. Well, I don't care when, equals 0.5 meters per second that way. Still the same. Now here's the deal. Well, what if, instead of we're standing around on the floor here in the lab looking at these objects move like we typically would, what if we looked at each of those objects from the frame of reference of that moving center of mass? So it's almost like, all right, here's this object moving at 2 meters per second to the right. Here's this object moving at 4 meters per second to the left. But what if we're literally like riding on some other object that happens to be moving at that velocity, 0.5 meters per second to the right? Well, if we did that, it's kind of like saying, okay, here's a car, and that car is going 40 miles an hour that way. And we're in a different car, and we're going 20 miles an hour this way. Well, relative to you in here, it looks like this car is going that way at 20 miles per hour. It really is going 20 miles an hour that way relative to you in that car. All right, so if we talk about the velocities of these objects relative to the center of mass, or from the center of mass frame of reference, let's see, frame of reference goes to the right at 0.5 from a stationary lab reference frame that moves at 2. So this is, well, this object would have a velocity relative to the center of mass frame of 1.5 meters per second. If the center of mass is moving to the right at 0.5 meters per second, and this object is moving to the left at 4 meters per second, well, from the frame of reference of the center of mass, it actually looks like this object is moving to the left at 4.5 meters per second. And we're doing some complicated stuff here, right? With locating centers of mass, finding center of mass velocities, and all. This I find to be the part where it's probably easiest to goof up, just doing these relative velocity things. But here's what's cool about this. All right, what this says is, if we look from this frame of reference, well, what's the total initial momentum? Well, it's 6 times 1.5 is 9 kilogram meters per second this way. 2 times 4.5 is 9 kilogram meters per second this way. Well, it's 0. Well, of course it is, because we're saying, what's the system's momentum relative to the system, right? The center of mass is the system, right? And we can approximate these two moving masses as one object that's at the center of mass. And what's that object's velocity relative to that object? It's nothing. So therefore, what's the system's momentum relative to the center of mass? Or from that frame of reference? It's nothing. And therefore, of course, at the end, afterwards, it's also nothing. Okay? Right. Now, here's where this can be of a bunch of help to us. And, here's from our lab frame. Here's what the objects are doing, how fast, what direction. from the center of mass reference frame, we said, this is just a repeat from before, that this is 1.5 meters per second this way, this is 4.5 meters per second that way. Well, here's the deal. The reason that we're doing this, the reason we're talking about this at all, is because we want to be able to investigate a certain special situation. That was not neat enough for my liking. And that special situation is we want to, we've done a lot of, I've used the idea of hit and stick, the inelastic collision, as a way to justify maybe, what the system does afterwards. But what we want to be able to do is talk about, what if they don't hit and stick? And what if they really don't hit and stick? And what I mean by that, notice here's my small print disclaimer down here. Let's assume that this is what we call an elastic. Sometimes I say perfectly elastic because I don't want to say anelastic where it sounds like inelastic. An elastic collision. And the criteria for a real elastic collision is the objects can't actually touch each other. And the reason they can't touch each other is because we don't want to have this. Here's cart 1, here's cart 2. There's their collision. Well, that can't be a real elastic collision for us. And the reason is we don't want that. And what we don't want is some kinetic energy turning into some sort of other kind of energy. All right, so what we're saying when we say, well, this really perfect elastic collision in which things don't even actually touch each other, which is possible. Typically, I mean, especially if things, have some magnetic repulsion or some electrostatic repulsion like charges would. They don't touch each other, but they can exert forces. All right. If that happens, well, I don't care what kind of interaction it is. What's going to happen is the net change in momentum is going to be 0. That's true no matter what. But for this perfect kind where things don't actually touch each other and we don't get any of that whack, and we don't get any surfaces or objects changing temperature and heating up, we don't lose any kinetic energy. So what we get is a net change in kinetic energy of 0. So this says, of course, momentum is conserved. This says that kinetic energy is conserved. All right? So from the frame of reference of the center of mass, here's what was initially happening. 6 kilogram moving this way, 2 kilogram moving that way at those speeds. Well, what we have to do is satisfy both of these criteria. We have to have afterward, the same amount of momentum. We have to have afterward the same amount of kinetic energy. And there's only one way to make that happen. And that way is that the 6 kilogram turns around, comes back in just like it was. 2 kilogram comes around, turns around, goes back out just like it came in. All right, and here's what you can sort of think about. The center of mass as this point in the middle of these that doesn't move. Right? Because again, these are the velocities of these objects relative to the center of mass velocity. So the center of mass, imagine it sort of like, well, an infinitely massive object that doesn't go anywhere. Now, I understand that the center of mass is not a thing, it's not an object, but if we think about it as something that doesn't move, well, then this 6 kilogram object comes at it, and the thing can't move, so it has to bounce back just like it came, or we would have either lost some kinetic energy or gained some. The same thing can happen, or does happen, for this 2 kilogram object. It comes in like this. It can't lose any energy. It's got to go back the way it came after it hits this object or this, this place really that can't move at all. It bounces back without losing any energy. And what we get here is this final situation where we've conserved momentum. There's still 0. Oh, and I haven't even proven that. Let's look at this. Well, I did prove it, right? On the last page? Yeah, sure. We proved that here. So we've got the case, we've met the criteria where initial momentum is 0, final momentum is 0. Well, let's see. Let's look at initial kinetic energy. Well, KE initial, 1/2 mv initial squared plus 1/2, this 1/2 mv squared plus this 1/2 mv squared. Well, let's just see what that is. Well, can you buy it? Of course you can buy it. The speeds haven't changed, right? No speeds changed anywhere, and masses haven't changed. It's still 6 moving that fast. It's still 2 moving this fast. So of course the kinetic energy is conserved. Okay? Now, the last little step here is, again, here's our center of mass reference frame. This thing, 1.5 meters per second this way. This thing, 4.5 meters per second that way. What we'd like to be able to do is talk about this in the standard, what we call lab reference frame, or what some people would say is as seen by a stationary observer. What are these objects actually doing? Well, remember, the center of mass velocity is 0.5 meters per second that way. All right, so you're in a car moving to the right at 0.5 meters per second. It looks like something is coming at you at 1.5 meters per second, or going to the left at 1.5 meters per second. What that means is, relative to a stationary observer, this has a speed or a velocity of 1 meter per second to the left. All right, you're in a car moving at 0.5 meters per second to the right, and it looks like something's moving at 4.5 meters per second to the right. Well, what that actually means is, relative to a stationary observer, it must be moving at 5 meters per second to the right. Okay? And, well, I mean, this is what happens. This is what happens. This is the end state of two objects of these masses, starting at those speeds, that undergo this certain special perfect kind of interaction, collision. They bounce apart, and this is what happens. That's the only thing that could possibly happen, as long as it's this perfect kind of collision. They have to have those two final velocities. All right? And let's see, we could say, well, in the final, the net final momentum here is, let's see, we got 6 kilogram meters per second to the left. We have 10 kilogram meters per second to the right. That is 4 kilogram meters per second to the right. And, oh yeah, look. That's what it was initially. We said, I just know that's what it has to be at the end, but based on our combinations of masses and velocities here, we've proven that it is. Okay? All right, so you will try this one. You should try this one. And I recommend the following process. That process is, first, find the center of mass velocity. Here's the tricky part. Sort of translate these two velocities into what they are in the center of mass frame. Excuse me. This is the easy one. Find what their velocities are after the interaction in that frame. That's the easy one. And then another tricky one is translate these two final velocities back to what we call the lab frame, what a stationary observer would see. Okay, and what you can do when you get this right is, I checked this before, and I think, actually I'm sure of it, but if we look initially, 1/2 for times 12 squared. That's 2 times 144. 288 1/2 mv squared. 3 times 9, 27. Yeah, the KE initial is 315 joules. All right? It better darn well work out that KE final is 315 joules. So after you go through this process and end up with what the final velocities of the objects are, back in the lab reference frame, just confirm that the final kinetic energy is the same as the initial. Because that's how we got to this. And that's the big criteria, or one of the two big criteria, that allow us to, well, go from here to here. Okay? If I see you Monday, you will have this, or if I see you next time, you will have this completed. I look forward to it. Adios.